Good? Live.
Okay. Oh, live. Okay. So now I gotta watch out. So. Yeah, good.
Okay, so we continue with Chan's third lecture.
Okay, well, thank you very much, and good morning, everyone. Nice to see you all again. So today I will continue the story, and I spent sort of 2 full lectures almost on motivation, and it's very important that I did that, I think, because today we're going to do something seemingly completely crazy, but hopefully after the 2 first lectures you will be more motivated to trust me and come along on this ride with these bizarre constructions that we will make. And hopefully you'll see also mirrored some of the steps particularly that we saw in lecture 1. So remember that our goal was to transpose as much as we could of the theory of singular moduli, so special values of the J function at Cm points, but for real quadratic fields. And of course, if we approach this naively, we immediately see that we can't trust our J function anymore, because our J function has as its domain, and I was given lots of nice bright colors today, so I'll try and use as many as possible. If this is my upper half plane, then the J function is of course a complex analytic function from this upper half plane to C, and we were able to evaluate it at Cm points by definition of Cm points in a way. And that's because the prime infinity is inert for any imaginary quadratic field. So that means my Cm points, I can always find them with positive imaginary part, and they will lie very nicely in the domain of the J function. If I try and change this to solutions of quadratic equations with positive discriminant, of course, again, by definition of a real quadratic field, we have some problems, because the Rm points, by which I mean same kind of definition, solutions to quadratic equations with integer coefficients, but with positive discriminant, they lie just outside of the domain of the J function. Yeah? So that's a very basic kind of observation, but which shows, in some sense, the key obstacle. And the key obstacle here is that these 2 types of quadratic fields are distinguished by the splitting behavior of the prime infinity in them. Yeah? Here infinity is inert, here infinity is split by definition. That's one way to view it. And so the key underlying kind of switch is, well, sorry, I get confused. There's too many colors to choose from, so I can't pick. But the key changes that we will make is that we will switch in this whole theory the infinite prime to a finite prime p. We now have the flexibility to choose that finite prime p such that it's inert with respect to the real quadratic field that we're interested in. Yeah? So we can hope to have a symmetric space where we have a large supply of Rm points. Now, unfortunately, that's not the only thing we will switch. We will also switch in this whole theory an H0 to an H1. So we will go 1 degree up in cohomology in a way that I'll explain to you more clearly later on. So we will switch from H0, which is roughly sort of invariant functions, so think SL2Z invariant functions like the J function. We will switch them to cohomology classes in H1 for the same group with coefficients in the set of meromorphic functions on the p-adic upper half plane. So that's a sneak preview of what's about to happen today. Okay, so what I want you to keep in mind is from the very first lecture that there were 3 key steps that we saw and explored in a variety of setups. So the 3 key steps, which we'll see again today, is the first step is we will construct an additive cocycle. So think of something that defines an element in some H1, which has the property that it has simple poles and integer residues at those poles. Just like what we saw in the very first lecture, we saw that, for instance, the cotangent function, we had this sum of 1 over z minus lambda, was lambda ranged over our group. This kind of thing will be replaced here with a cocycle with the same kind of properties. And then we saw, once we had this cotangent function, we found a multiplicative lift for it under the logarithmic differentiation map, and that's what gave us the sine function. So that second step, again, we'll come back today, and we will construct a multiplicative lift of these cocycles for the logarithmic differentiation map. And then the third thing that we will do today, and that's perhaps somewhat mysterious at this point, is that, well, I can tell you we go from H0 to H1, but then it's not at all clear what to do with an object in H1. If I have a function in H0, like the j function, I can evaluate it at a point. It's a function. If I have a cocycle, it's not so clear how to evaluate a cocycle. It's like a collection of functions. And so I have to explain to you also, and I'll do that today, how you can still meaningfully evaluate these multiplicative lifts, these cocycles, at least at Rm points. So those are the 3 things that are about to happen today. So let's try and make these a little bit more precise, and let me explain exactly which H1s, etc. So very general notation is I can put myself in the following setup where G is some group and M is a left G module. It's an abelian group with a left action of this group G. What I can do is, whenever I have such a gadget, I can define the set of cocycles for G with values in this left G module M to be the collection of functions from my group G to my module M that are almost homomorphisms. Yeah? So they satisfy the so-called crossed homomorphism identity, which means that if I evaluate phi on the product of 2 elements in this group G, then I get almost the sum of the evaluations of phi at the 2 individual elements, except I have to act by the first element on the image of the second element under phi. Yeah? This is sometimes called a crossed homomorphism. Okay. So it's a set of functions like this. So these are the 1 cocycles. Now, how do you construct such a 1 cocycle? Let me tell you a particularly easy class of 1 cocycles that's very easy to construct. Those are the so-called co-boundaries. They sit inside of there. And they consist of all of the functions from G to M that have the property that they're of the form that I'm about to describe, namely there exists some element, let me call it M sub phi, and it's an element of M which has the property that phi of some element G is just given by letting the element 1 minus G act on this M phi. So if you haven't seen this kind of construction before, check that this is indeed a subset of Z1. So check that this verifies the co-cycle identity, which is quite easy to see. Okay. All right, so these are very naturally abelian groups, and the quotient, so define, or depends, if you already know a definition of the first group cohomology, then this is a result, otherwise it's a definition. So H1 of Gm will be the quotient of the cocycles by the easy ones, which are the co-boundaries. So the H1 measures sort of all the interesting cocycles that we can make, where we modulo out these easy ones that are very elementarily constructed. Okay? So that's what the first group cohomology is going to be. So this is completely general. I just took a group and a left G module, but of course we're going to specialize to setups of arithmetic interest. And that's what I'll do now. And in fact, I'll spend almost the entire lecture on the case where G is SL2Z, even though the construction of Rm singular moduli requires a different group, namely SL2Z1 over P, where we invert also P. But I choose to focus on SL2Z because the ideas are really, and even the definitions are really exactly the same, and it allows us to explore them in a much more familiar setup, even though the invariants are a little bit poorer. So I think it clarifies the ideas a little bit to restrict to that setup, at least for the time being. Okay, so in every construction I make, you should feel free to change SL2Z to SL2Z1 over P. And if you're willing to believe that things converge, the constructions are precisely the same. So nothing really changes. Okay, so rational cocycles. So rational cocycles will be a specific instance of this construction that I've made here. So there'll be specific elements in this Z1GM, where G will be the group SL2Z, 2 by 2 matrices with determinant 1 and integer entries, and M will be the module of rational functions in one variable. Okay? So fractions of two polynomials in a variable Z. And I have to tell you how this acts. So this needs to be a left module for this group SL2Z. And the action is given as follows. So if I take a matrix A, B, C, D in SL2Z, then I'm going to make it act on my rational function f. It needs to be a left action. So I'm going to act on the argument by linear fractional transformations by the inverse of this matrix. So that's dz minus b minus cz plus a, like so. And I'm going to consider the weight 2 action. So I divide this out by minus cz plus a squared. That's the definition of my action. Okay? So if you're familiar with the theory of modular forms, this perhaps doesn't look all that strange, except I'm acting on the left instead of on the right, so that's why the inverse appears, but other than that, it's precisely the same. So here we're acting on rational functions. So M now is a left module for this group G, so I can form these cohomology groups, and I can wonder, is there anything interesting in there? Yeah? Okay. Okay, so here's an exercise for you of one cocycle that's not particularly interesting. It's a bit too degenerate, but it's a great way to absorb the definitions. If you haven't seen this before, so here's an exercise. And that's the example of what I'll call the Eisenstein cocycle. And the example is the following. So I'm going to make a choice first. I'm going to choose some base point B. And what is this base point? This base point will be an element of P1 of C, yeah, the projective line with complex entries, which I'll denote by a homogeneous pair of points U, V, yeah, where I say U1, V1 and U2, V2 are the same if they're the same up to rescaling. Okay? So these are homogeneous coordinates. So this is my base point. Given such a base point, I'm going to define for you a function from the group to the module And then your exercise is to check that it's a cocycle. Okay. And the function is the following. I'll call it P sub B. And P sub B, since I'm in this setup, G had better be SL2Z, and M had better be CZ. And I'll tell you what this function is. I take a matrix gamma, and I send it to L of B, and I'll tell you what that means in a second, minus L of gamma B, where gamma just acts on B in the usual way. So it's a 2 by 2 matrix acting on a column. Yeah. Okay, so now I have to tell you what L is. So if I take L of some element in P1 of C, roughly it's 1 over Z minus that element. Yeah. But because that element could be infinity, I have to tell you what I mean when I'm dividing by infinity, etc. So let me take this more robust definition, that if I take L of some projective point on P1, then that's defined to be S divided out by SZ minus R. Yeah. And so we see that if I rescale Rs by some scalar, this function is invariant, yeah, because I scale the numerator and the denominator by the same element. Okay? All right, so that's my function. It's a well-defined function from SL2Z to the rational functions. And your exercise is check that it's indeed a cocycle. So prove that this PB is indeed an element of Z1 GM by checking the cocycle relation, and check also that it's kind of independent of B in the following sense. So it depends on the base point B only up to a co-boundary. Meaning that if I change my B to some other B prime, I change my cocycle by something in this module here, B1. Okay. So in some sense, it doesn't depend on B, or more precisely, the cohomology class doesn't depend on B. Yeah? So what we get out of this is something we might just call P without the sub B, and that's a class in H1 GM. So H1 SL2Z CZ. In fact, if you're brave, you can extend the exercise. It's not so difficult, but you can show also that it's not zero. So it's not the trivial element in this cohomology group. In other words, that function that I just defined for you is not a co-boundary. Yeah? Yes?
Can you repeat what you said about changing B?
Absolutely. So if I pick two different B's, so let me write it here actually. So i.e., if I take a P sub B1, first base point, and I subtract P sub B2, then I land inside of B1 GM. Okay. Sure. All right, so there's many ways to go about this exercise. The least inspired way is to just calculate. And you'd be surprised at how unpleasant this is, even though it looks very simple. You're not going to be happy from it, but you might prove it. So that's option number one. I recommend doing it just to appreciate that some kind of miracle happens in the definition. It's not so easy to write down a cocycle. This is one way to do it. I'll tell you another one in a second, which is less, a lot less trivial than this one. And then, in fact, there's a theorem that says those are the only two things you could have done, in some sense. So it's very difficult to write down a cocycle, and doing the calculation will make you appreciate which miracle occurs. Nonetheless, the calculation is kind of unenlightening, and if you wanted to construct new examples, you wouldn't learn much from this calculation. So a second way, and that's maybe a hint I can give, is you can think about why I called this the Eisenstein cocycle. And there's a little hint hidden in that. If you can relate this cocycle to the Eisenstein series of weight 2, you'll have a very easy proof of this statement. So in fact, if you allow yourself to change the module M from rational functions to functions that are more complicated, like the Eisenstein series of weight 2, then it becomes a co-boundary, and then it's easy to show it's a cocycle. So that's my hint if you want to challenge yourself and prove it maybe the proper way. There's also a third way, using modular symbols. I don't really have time to explain that today, but if you're interested in that, there's a set of notes which I sent to Hector and I think will be posted on the website at some point, which contains in more detail all of the things I'm going to say today and tomorrow. So you can read there, and there's more exercises and there's more extra material, so you can see various ways, in fact 3 ways to prove this theorem. But it's better to try first yourself and then look at the notes. You'll learn much more that way. Okay, any questions about this strange Eisenstein cocycle? By the way, if you told me, okay, now give me an example, pick a base point, which base point do you think I will pick? Yeah, infinity, right? That seems like the easiest one. So if I pick infinity, that's 1 and 0 here. Yeah. So what's L of infinity? That's 0. Yeah. So L of infinity already doesn't appear. So all that's left is L of gamma infinity. And L of gamma infinity, if gamma is of this form, what's gamma infinity? It's A over C. Yeah. So you see that here you just get 1 over Z minus A over C. That's why you send gamma. So that's a very simple way to describe for that particular base point what it is. Okay? So that's the nice thing about this. It depends only up to a coboundary on this choice of base points, so I can pretty easily switch between them. Yeah. Okay, anyway. Here. Okay, now this cocycle, in fact, let me tell you a secret about it. If I change the group to GL2C, and take the same definition, it would still be a cocycle. So that gives you a hint that there's not a huge amount of arithmetic in this cocycle. It's too general somehow. And you'll see that in your proof also. When you do the calculation, you could extend it to this much bigger group. So there's nothing really arithmetic about it. The fact that we're working with SL2Z doesn't give us a finer cocycle or anything. So it's more of a geometric kind of thing. Whereas the cocycle I'm about to write down, which is really the main example in our whole construction, is really arithmetic. And it's a very strange thing. It's called the Knop cocycle. So the main example for us is what I'll call the Knop cocycle. And that's because it was first constructed by Marvin Knop in the 70s. For reasons that I never understood, but he did find this object. But for us, it'll serve a very crucial role. So let me explain to you what this object looks like. So the Knop cocycle, it's going to be an element of Z1 SL2Z with values in CZ. Yeah? So it's going to be like the Eisenstein cocycle in that same cocycle group. But it depends on the choice of an Rm point, or equivalently, a quadratic form Q inside of the set. Oh, did I define this last time? No. Okay. So this is the set. So the set of primitive quadratic forms ax squared plus bxy plus cy squared, where a, b, and c are all integers, yeah? And primitive means that they don't have a divisor in common. Yeah? And the sub delta there means that the discriminant is equal to delta. Yeah? Okay, so it's a huge infinite set, but up to SL2Z equivalence, this is a finite set. This is the class group of Q joined the square root of delta, roughly, the narrow class group of that field. Okay. Now, in fact, this is a little bit more general than the statement I just make. So I will just take this same definition, but with delta not necessarily a fundamental discriminant or something. So delta is really just a positive discriminant. It can even be a square. Yeah? So it can even be a degenerate quadratic form that splits over Q. That's also fine. Okay. Now, associated to such a quadratic form, I will go back to my picture of the J function, the domain of the J function, and I'll define a geodesic that lies inside of the domain of the J function. Yeah? So I'll define geo of Q to be the geodesic connecting the roots of Q. So let's draw a picture of that.
Am I supposed to think that these ABCs are the same as?
No, they're completely unrelated. So sorry that I used the same notation here, but no, they're not related.
The question you said that this set is almost the ideal class group. What do you mean by that?
Yeah, so let's say that delta is, well, it doesn't actually matter all that much. For any delta, the following statement is true. If I take f delta and I quotient out by the action of SL2Z, which I didn't define for you, but it's the action, the usual action on quadratic forms that, for instance, Gauss was considering, that's a very nice right action. And so if I take f delta modulo SL2Z, that's a finite set. And in fact, that finite set has a natural bijection with the class group of the quadratic order of discriminant delta. And that gives also the quotient here a group structure. In fact, Gauss was not aware of the right-hand side. He didn't think in terms of ideals. He thought purely in terms of quadratic forms, and he defined the group action on quadratic forms. This is the famous Gauss composition. So it has a group, it's a finite set, but it has a group structure. Anyway, there's much to say about it, but it doesn't matter all that much. Okay, so what's this geodesic? The roots of Q, in fact, I can label, there's a preferred root of Q. There's two, of course, it's a quadratic equation. One I'll call RQ, and that's the same RQ I defined last time on the board. That's minus b plus the square root of delta divided by 2a. So that's the root where I choose the plus sign in the quadratic formula. And the other one, its conjugate, will be RQ prime, yeah, the conjugate of RQ. And so if I take these two, there's a geodesic in the upper half plane that'll look like a semicircle, like so. And it even has a canonical orientation if we agree that I'll always orient from the conjugate to the preferred root, like I drew in the picture. Okay. So that's this geodesic. So this is in the upper half plane. I didn't say this, but okay. Now, whenever I take some random points x and y in the extended upper half plane, so h star will denote the extended upper half plane, which means h, the upper half plane, together with the cusps, so p1 of q adjoined here. Now, I say x and y need to be random points, and random is meant in a very specific sense, in that I don't want x or y to lie on this geodesic or any of its SL2Z translates. So I want to stay away from this kind of thin set that is defined for me by this geodesic. So I'll stay away from the set which is all the SL2Z translates of this geodesic of Q. Yeah. Okay. Then I'm going to make a definition. I will define sine sub Q of the pair x comma y to be 0, 1, or minus 1. And I want this to be the intersection of the geodesic defined by Q, which I drew here in orange, and the geodesic, hyperbolic geodesic, connecting x to y. Okay. So let's draw that. Oh. Let's use purple. So here maybe is my x. It's not on this orange geodesic. And then there's maybe a y, also not on this orange geodesic or any of its translates. And so I get a hyperbolic geodesic connecting the two. And the intersection of these two geodesics in the usual homological sense is going to be 0, 1, or minus 1. And that's what I call sine Q of x comma y. Yeah? So the purple one and the orange one. Now, who's left-handed in the audience? Ooh, that's a wild minority. So I will stick with the right-handed orientation in that case. Okay, so that means if I intersect first the geodesic of Q, I'm going to use my right hand. My index finger will follow along the orange geodesic. Then my middle finger will follow the purple geodesic. And then if my thumb points inside the board, it's -1. And if it points out the board, it's +1. And if they don't intersect, it's 0. Okay? So now that we all agreed on the right-hand orientation, we know what this means. Okay? It's a well-defined sign. All right. Okay, so now let's make a bizarre definition.
Here, h asterisk is upper half plane plus real line.
Plus P1 of Q. So the extended upper half plane, so just the cusps, yeah, just the rational ones. Okay, so here's a theorem from the 70s by Marvin Knopp. Okay, so again, just like with our Eisenstein cocycle, I'm going to start by choosing a base point B, and a priori I'll just choose it in the extended upper half plane. And I'm also going to choose a quadratic form F inside of this set F sub delta that I just defined for you, with delta greater than 0. Yeah? Now this base point and this choice of quadratic form have to be somewhat random with respect to each other, so you don't want to choose B in a stupid way, and the stupid way would be to choose it on one of the SL2Z translates of the geodesic. So if you stay away from that set, the definition is valid, so let me subtract that again. SL2Z times geo of Q. Yeah? So I have these two bits of input. The Eisenstein cocycle didn't really depend, well, it depended only on the base point. There was no additional input. And then we saw that in cohomology, it didn't even depend on that base point anymore. Here, the dependence on the quadratic form is crucial. Yeah? And so we'll get to that in a second. So you have to give as input already a quadratic form. Now what holds?
Q is F.
Sorry? Oh, sorry, yes, Q is F. Thank you. This might happen a couple more times. So keep me honest, yes, thank you. So I'm going to define a function for you, which I'll call Kn for Knopp, subscript B and F, my two choices that I made. And it's going to be a map from the group SL2Z to C of Z, as promised. And you can already see coming that the theorem will say whatever I write down is going to be a cocycle, yeah, and that's indeed the conclusion. Now the tricky part is what I'm about to write down. I'm going to take a matrix gamma, and I'll send it to the following sum. So now I'm going to sum over all Q's that are SL2Z equivalent to F. Yeah? And I told you in this set here, this may be strange, but so F is my quadratic form here. The notation is changed. But in this set of primitive quadratic forms, there's an SL2Z action, and there's finitely many orbits. Yeah? But every orbit is still infinite. There's an infinite amount of quadratic forms, and I'm going to loop over all of the quadratic forms that are equivalent under this SL2Z action with my original F. Yeah? So that's an infinite sum a priori. But this is what I'm going to sum. I'm going to sum the same function L that I had last time. L of RQ, so the first root of my quadratic form Q. So that's 1 over Z minus RQ, in other words. And I'm going to weigh that by the sine of Q of my base point as my choice for X, and for my choice for Y will be gamma times the base point. That's the definition. So I'm going to sum the L of R q's for all the q's that are equivalent to f. That's infinitely many. And of course, if I didn't put this factor, that would never be a rational function. There would be infinitely many terms appearing, let alone convergence, etc. This will never be a rational function. But if I put in this sign, it's usually going to be 0. That's part of the statement somehow, that this expression on the right is secretly a finite sum. Yeah? So it's a well-defined element of C of Z.
So it's sine of b gamma b.
Yes, b comma gamma b, indeed. Yeah. So if I choose my base point, the base point is fixed, but the cocycle takes an element gamma, and every time that's going to change the second base point here in my summation. Yeah? So it's going to be go from b to gamma b. Yeah? And so that's the geodesic that's going to vary as my element of the group varies. Yeah?
How are we choosing which routes to take?
So I always choose this one,
Oh,
the preferred route, where I choose the plus sign in terms of the quadratic form.
This equivalence relation is about getting the action of CL2Z?
Yes, precisely. In fact, if you like, I can write that on the board because I'll use that notation a couple of times, so it deserves to be spelled out. So i.e. Q is in the SL2Z orbit of F. Yeah, that's what that means. Okay.
So to measure this, oh, no, I'm so sorry.
Okay, no, that's fine. All right, so the end of the sentence is missing. Then this is a cocycle, yeah? That's the conclusion. So is in Z1 SL2Z CZ. Okay. And it's kind of difficult to appreciate these kinds of theorems if you haven't messed around with cocycles a little bit yourself. And I could go on for 4 hours explaining to you a little bit about this Knop cocycle. But if you mess around with it for a half hour, you'll learn much more. So, so for the proof, which I recommend to only look at after you've tried a little bit, see the notes. So see these notes that will be linked on the web page. And again, there are several ways to prove this. You could do it by a direct calculation, but it's horrible. It's absolutely unpleasant, but it can be done. Yeah? And so in the literature, it has been proved in that way. But there are better ways to prove it. I'm not going to prove it here. You can believe me on it, but the unfortunate aspect of skipping the proof is that it's hard to appreciate just how miraculous this is. It looks like such a random definition, but it's exactly tinkered in such a way that this gives us a cocycle. The cocycle relations are a very non-trivial thing to hold for a collection of functions. So it's quite difficult to write down examples. But Knop managed to do it in the 70s, and this is one way to do it. So we have our Eisenstein cocycle, and we have these Knop cocycles. There's one other kind of silly one, which looks like the Eisenstein cocycle. And then there's a theorem, actually, that says that all of the cocycles that have a similar property to this one, in the sense that they're parabolic, whatever that means, are of this form. So it's a full classification. A couple of comments about this. First of all, the choice of the base point is way less important than the choice of the quadratic form. Again, the choice of the base point, you can show pretty easily that it's there, the cocycle depends on it, but it only depends on it up to a co-boundary. So there's a well-defined cohomology class. Let me state that. And that cohomology class I will call Kn sub f, so I'll drop the dependence on the base point B. And that is a well-defined element of H1 SL2Z CZ. So the base point really doesn't matter, but the quadratic form is hugely important. Yeah? That really changes the behavior in a really profound way. Okay, so that's the Knop cocycle. Here's the definition, and you have to take on faith that this is indeed a finite sum and defines a cocycle, both of which are non-trivial statements, particularly the second one. The latter is quite non-trivial. So instead of the proof, let me just tell you about one example. And you can check a couple of identities that follow from the fact that this is a cocycle, which are highly non-trivial identities. And in fact, they're also key to the classification of these kinds of objects. So here's an example. And the example is, I'll take for f 1, 1, minus 1. Sorry, I didn't define this notation, but it's often convenient to write ABC for the form ax squared plus bxy plus cy squared, because that takes a long time to write down. Yeah? So this is x squared plus xy minus y squared. Okay? So this quadratic form has discriminant 1 squared plus 4, that's 5. So it's discriminant 5. And its roots are the golden ratio, essentially, or minus the golden ratio. Okay, so now I have to choose a base point also, but I already told you that's not super important. And if you ask me to choose a base point, of course, I'll choose infinity. And now, you see, it's a cocycle. So that means, how do I describe a cocycle? For every matrix, I have to give you a function. Now, there's a lot of matrices, so I don't want to be here all day writing all the matrices out. That wouldn't really work very well. But SL2Z is finitely generated. So if I tell you what it does on the generators, you'll know, in principle, how to extend it in full generality. So SL2Z is generated by two matrices, namely this one and this one. And traditionally, these are denoted T and S. Yeah, so that's the notation that I will use in what follows. Is orange fine in the back of the room? I saw some people squint, so okay, I'll avoid orange, yeah. Okay. So T and S. Okay. Now if I tell you what this cocycle is on T and on S, then in principle I've told you what it is on any matrix. Now on T, that's the easiest one. So if I take the Knop cocycle, I drop the notation of the base point, not because I'm just looking at the cohomology class, but because infinity is sort of implicit. So whenever I choose infinity, I don't write the dependence on the base point. So the value of this cocycle, I have to specify for you at T and S. And at T, it's very easy. What happens at T? Maybe someone can tell me what happens at T, actually. I choose my base point to be infinity. And if I plug in T, T doesn't move infinity at all. So this intersection is always 0. So I get 0. Okay. Great. Now, I hope something interesting happens here. Otherwise, all of this was for nothing. If I do it on S, you'll get something very different. Yeah? S of infinity, that's 0. So what we get here is the geodesic from infinity to 0. And now we're going to take 1 over Z minus RQ for all the q's that intersect that geodesic. So that's all the q's for which one of the roots is positive and the other is negative. And now you can kind of puzzle around and find all of those forms that are equivalent to this and have that property. And you'll find the following. You'll find square root of 5, some elementary factor. And then you find the function 1 over Z squared minus Z minus 1. And 1 over Z squared plus Z minus 1. So these are the functions that come out. So they're really rational functions. And in fact, when we just did this thing of intersecting with 0 infinity, you have forms where one of the roots is positive and one of the roots is negative. That means that A times C is negative. And if A times C is negative, then B squared minus 4AC tells you that B is limited in options because delta is positive. And so from that, you can already puzzle together why this is a finite sum. So anyway, but that's just an aside. Okay, so this is still, they form part of a cocycle, and that's a highly non-trivial thing. If I tell you some random values for T and S, of course that's not going to be a cocycle. They have to satisfy very strong identities. And the strong identities here you can check for yourself. They come from the presentation that you write down for SL2Z. I just wrote down the generators, but the relations will tell you that in fact these functions, this one is 0, so that doesn't need to satisfy much, but this K and S here needs to satisfy that if I act on it with my left action by 1 plus S, then I get 0. And if I do the same with 1 plus ST plus ST squared, then I also get 0. And these are highly non-trivial identities to be satisfied. In fact, whenever you have a function that does this, it comes from a cocycle, and that's key to the classification of these things. All right, so now that we have this Knop cocycle on board, notice these L functions here. I say L functions, they have nothing to do with L functions, but the functions which I called L, so 1 over z minus rq, have precisely that same property that we recognize from the cotangent function and whatever it was, the zeta function, Weierstrass zeta function. They have simple poles, and the residue is always plus or minus 1, because that's that sign. Always plus or minus 1. So that means we can dream of finding a multiplicative lift of these cocycles for the logarithmic differentiation map. And that's precisely what we're going to do.
Can I ask something?
Yes, yeah, please.
So this
Oh.
construction only depends on the class of F, obviously.
Yes.
Is this map injective? Like different classes go to different H1 elements?
In general, I wouldn't stick my neck out to say that. No, I would stick my neck out to say that, yes. Yeah, they are.
And is there a relation between the group law in the quadratic forms with the group in the H1?
No. No, not that I know of. No, in fact, that's definitely false, yeah. Yeah.
And here you always get like the, I think these are called like the reduced forms in the cycle of.
Yeah, kind of, yeah, they're nearly reduced. So reduced has an additional condition. So Gauss defined reducedness of a quadratic form ABC. So ABC is reduced for positive discriminants. Gauss said that this is the same. I mean, in fact, this is a different way of interpreting his criterion, which was a little bit messier, but it's equivalent, in fact, to this condition. So this is reducedness. Whereas the one we see don't have that second condition. So they're nearly reduced in the sense that A times C is less than 0, which is equivalent to saying the roots have opposite signs. Yeah? And there's always finitely many of those. Yeah. Okay. All right, so the multiplicative lifts. So for the multiplicative lifts, we want to consider now the module of multiplicative functions. So it's still the same rational functions, but I take only the non-zero ones, and I take the group law to be multiplication, not addition. And the action will be the weight zero action. So meaning if I take A, B, C, D, and I act on F, that's the same as F of dz minus B minus CZ plus A. No automorphy factor here. So weight zero action. Yep. And the question is, can we lift our cocycle for the following map? So I have a natural D log map, which I defined in the first lecture, that takes me from a cohomology class multiplicative in this sense to a cohomology class, the additive cocycles that we just studied. And I've already told you we've constructed lots of interesting examples here. We have all these Knop cocycles here. Yeah? And the question is, can we lift them for this logarithmic differentiation map to something which we might call multiplicative Knop inside of here? Yeah? It maps to that under the natural D log map. Now, in general, this can be a pretty subtle question, but in the setup that we're considering here, actually, that's not so difficult. Yeah? And the first observation, and this is kind of also what we saw before, is that with our infinite sums in the very first lecture, finding a multiplicative lift was kind of easy. We just wrote down the corresponding products, yeah? Where the residues that we had on the poles became the exponents of the function. And that's always a multiplicative cocycle up to scalars. So we lost the invariance in general. There was always some kind of scalar periods coming out. They were quite innocent in that case. We had the -1 for the sine function, and then for the sigma function we had this kind of exponential factor, but it was still fairly innocent. Here the same thing happens, right? So it's easy, using precisely the same procedure we've used time and time again, to lift modulo constants. Namely, we could just write it down with the same expressions. So I can write down the map that sends gamma to the product of q equivalent to f of z minus rq raised to the power sine q b gamma b. If you take the logarithmic derivative of that, you get back the Knop cocycle. And we already checked that that's a cocycle, so we know that the only way that this could fail to be a cocycle is by something in the kernel of the d log map, and that's a constant. So we know automatically that this is a cocycle for SL2Z, not with values in this module, but at least with values in CZ star modulo C star. So it can fail to be a cocycle only up to a constant. So that's the easy part. And then in general, you have to work pretty hard to see if you can lift it any further, except for SL2Z, you don't have to. So, in fact, let me write that here. That's how short the argument is. So for abstract reasons, this is enough. Why is that? Well, because if we look at the group where we want to be, H1SL2Z CZ star, and we take it modulo constants, so that's H1 SL2Z mod CZ star modulo constants, we've now constructed something in here, and we hope that it lies in there, and we know that this is part of an exact sequence where the next term is H2 SL2Z C star, and the previous term is H1 SL2Z C star. So there's an obstruction to lifting which lies in H2 SL2Z C star, and then we know if the obstruction vanishes, there is a lift, and the ambiguity in finding such a lift is measured by this group. Luckily, these two groups are essentially trivial. So this one is actually 0. That comes from that presentation of SL2Z that I wrote down. So you can check this as an exercise. If you know a little bit more about cohomology, for instance, I haven't defined H2. But if you do know what H2 is, try and check that this is indeed 0. And this guy is almost 0, so it's Z mod 12Z. Yeah. Which means that if a lift always exists, so this guy lifts to something in here, and that lift is actually unique up to multiplication by a 12th root of unity. Yeah. Okay? So that's it. So SL2Z isn't really rich enough to have interesting lifting obstructions. And we now see that we can lift our cocycle, or Knop cocycle, to an element in here. So this question has an affirmative answer.
Sorry, a question?
Yes.
Before your, is there always like a closed formula for the value of test?
Yes. The closed formula is actually pretty much what I said before. So the closed formula in general is that this is the sum over all q equivalent to f of z minus rq raised to the intersection of these two. And the intersection of these two I can make even explicit. So instead of writing q, in fact, let me do it even better. Let me write abc for q, and let me write rq is just minus b plus square root of delta divided by 2a. And then I have the condition that a times c is less than 0. This is already a finite sum now, and then the sign of intersection you can check will just be the same as the sign of a. So all you have to do is enumerate this set and then add up these guys. And so in this particular instance, there's 4 elements in this set. There's 4 terms. And if you add them up, you get this. So it's a rational function of degree 4 in the denominator. Yes. Okay. Now, we've done the first 2 steps. We constructed not a function but a cocycle, nonetheless, something with simple poles and integer residues. We then lifted it for the d-log map, which we did kind of abstractly, so it wasn't super explicit, but we know such a lift exists. And the last thing we have to do is evaluate it.
So when you say the cocycle, you don't mean this formula?
No. So this formula sits in here. But we know that because the lifting obstruction is 0, it always comes from something in here. So I can add on some constants somehow on all of these functions for every gamma so that it becomes a cocycle on the nose. What those constants are, I didn't tell you, right? That's a different story, but we know they exist. Yeah. Yes?
Do you always get a rational function with coefficients in the quadratic field, as in this example?
Yes. So this is a non-trivial result. So for the Knop co-cycle, this is clear, because by definition, this is true. But in fact, if you take any parabolic co-cycle, parabolic meaning if you restrict to the subgroup generated by T, you can find a representative where that's 0. This co-cycle has that property. Then, in fact, these are the only examples. That's a result of Choye and Zagier from 1993. Yes. Which is already a miracle, right? I mean, this cohomology group doesn't say anything about quadratic fields or anything, but somehow that's the only way to construct an example. Yeah. Okay. All right, so third step and final step in this expedition. We want some singular moduli. We have to find some values. And if you have a function, it's clear how to get a value. But if you have a co-cycle, that requires some justification. So what we're going to do now is we're going to take, first of all, a quadratic form that defines for me the co-cycle, and then, second of all, a quadratic form at which I'll evaluate it. So there's really a pair of quadratic forms that goes into the discussion. Just like in Gros and Zagier, j tau 1 minus j tau 2 involves a pair of Cm points. Here we get a pair of Rm points. Yeah, so like so. And let's just say that even though it's easy to extend this, let me just take them to be positive and let's say distinct. But you can imagine what happens when they're not distinct and it's the obvious thing. It's just not very interesting. Or not necessarily. Okay, so now I have to define a value for you. So I will want to take my Knop co-cycle associated to the first quadratic form, and I want to attach a meaningful evaluation to it. And that's what I'll denote by this. Now, how do I do that? Well, you see, the co-cycle is a collection of functions. I get a function for every matrix. So I'm going to evaluate this co-cycle at a very particular matrix coming from the argument F2. And that matrix is going to be a generator of the stabilizer. So stabilizer in SL2Z of F2, because we're dealing with quadratic forms with positive discriminant, is always of rank 1. So that's plus or minus 1, some gamma of F2 to the power Z. In fact, there's a canonical generator for it, usually called the automorph. Okay, so I take the generator of the stabilizer of F2, I plug that into my co-cycle. Now I have a function, and that function I evaluate at RF2, the root of F2, my Rm point. Okay. Now I get a value in C. Yeah. It's an actual complex number. The only thing that's not clear is if this bizarre definition makes any sense at all. And let me tell you two ways in which we might be encouraged that this is a good notion to consider. The first is that this is independent of the base point, which I've dropped from the notation anyway, so it better be true. Yeah, meaning if you take a co-cycle here that's cohomologous to it, so it differs by a co-boundary, I get the same value. So co-boundaries evaluate trivially. That's the first clue that maybe something goes right. But the second clue is much more important. This value is in fact SL2Z invariant for both F1 and F2. And as Sebastian noticed, for F1, that's clear to see from the definition, because the index set is kind of just on an SL2Z equivalence class. So it doesn't matter which F1 you plug in. But even F2 doesn't really matter. If I change F2 to gamma F2 for anything in SL2Z, that's still the same value. And that requires a check, but it's true. So it behaves formally just like j tau 1 minus j tau 2. It doesn't matter which tau 1 and tau 2 you plug in. It's SL2Z invariant. Yes?
Do we do this definition for the multiplicative?
Sorry, yes. Thank you. The multiplicative one, yes. Otherwise, I could have skipped the second step. For the additive one, it's not, the second one is no longer true. Yeah. For the multiplicative one, it is, and that's because of the weight zero action. Okay. So anyway, so the conclusion of this is that we've gone through all the motions for a group that's not really still the group that we want, but nonetheless, this already contains all of the ideas. And in the end, we might wonder what we've constructed because we get a canonical collection of algebraic values indexed by, well, the narrow class group of discriminant delta 1, because I told you that this SL2Z invariant for F1, so it goes through the quotient of all of these forms by SL2Z, which is the narrow class group of D1. And then I take the narrow class group of D2, coming from the fact that my argument, again, can be changed by SL2Z. And out comes some number. And if you think about this, these things are always rational functions with all of their zeros and poles inside of the field coming from F1. And then I evaluate at a root in the field coming from F2. So I never leave the biquadratic field that is spanned by the two quadratic forms. So let me call that L, get L star, where L is precisely as in the diagram we saw before, the biquadratic field spanned by K1 and K2, where K1 is generated by the root of F1 and K2 is generated by the root of F2. So indeed, we've constructed a canonical finite collection of algebraic values, but no one would say these values are particularly interesting at this point. They're just in the biquadratic field. A singular modulus lies in some abelian extension and it escapes the biquadratic field, whereas these are stuck in the biquadratic field. And that's because the sums we're considering are always finite sums. Yeah. Yes? Sure, go ahead.
What was gamma to mean? Could you please remind again?
Say again? This one?
F2.
Yeah, it's defined here. So I take the stabilizer of F2, my second quadratic form, in SL2Z. Because this is an indefinite form, this is an infinite cyclic group up to plus or minus 1, and I take a generator for it. In fact, there's a canonical generator for it.
That's class group. So how do you exactly get value from the product of two class group to F?
Yes, that's because the dependence here. So in fact, let me write it like this. That's clearer, I think. If I take F delta 1, all of the quadratic forms of discriminant delta 1, and I quotient out by SL2Z, that's precisely the narrow class group of discriminant delta 1. And this SL2Z invariance, and the same is true here, of course, right? So this SL2Z invariance proves that, essentially. So initially, I get a map from F delta 1 times F delta 2 to L star, but in fact, it's a map from the two quotients. So it's a finite collection of values that I get at this point. Okay, I'm out of time, unfortunately, but let me, oh yes, sorry.
You defined the multiplicative key in F1, but here you said that we don't have actually a lift, but we have this surjected to
Yes.
that gives us elements such that lifts the original. But we need to make a choice, right?
We need to make a choice. That's a good observation. The lift is not unique, but it's almost unique. It's unique up to a 12th root of unity. So there's two options that we have. Either we don't care about this 12th root of unity, we make any choice and we do this. There's three options we have. The second option, besides not caring, is to raise this cocycle to the 12th power, and then the ambiguity goes away. And the third option is to try and do a little bit better by identifying a canonical lift inside of here. And in fact, that's what my master's student, Felix Kalker, did. So let me tell you just in one word what he did, because you might wonder, what is this? It's a finite canonical collection of elements in L star. It's a little bit bizarre. I can't think of, what would these finitely many chosen elements of the biquadratic field be? It's very bizarre. And so my master's student has related these. So Felix Kalker has related these values, which are not yet very interesting, but nonetheless a little bit intriguing, to quantities that have been studied in the literature before. So they're related to the integral over the geodesic of F1 of the J function, where this geodesic lies in the upper half plane, and the J function, of course, is defined in the upper half plane. So I can make a geodesic integral over a fundamental segment of this geodesic, and out comes some number. And so it's a line integral of the J function. In fact, these have been studied quite intensely in the literature, starting with Kaneko, maybe early 2000s, but then lots of people have been studying them. And the hope was, I think, that they would find some algebraic numbers here, because that would be one other way to try and address the goal that we set out to solve today. We can't use the J function anymore because the Rm points are outside of the domain, but we can still make this geodesic and integrate the J function over it. Maybe we still get something that resembles a singular moduli. And people had hoped, I think, that this would yield algebraic numbers. Instead, it's yielded tremendously interesting invariants, but no algebraic numbers yet. So it's still a bit of a mystery, I think, where the algebraic numbers lie. Now, my student here has related this. There's two quadratic forms at play. And I've only used one, and that's because it goes on. I take the difference of two of these. Jz and then dz over f2z. So these quantities, if you've heard of them before or seen them in the literature before, have a relation to these evaluations of the cocycle that I made. But the relation is not something that makes anyone particularly happy. It says that the log of these is equal to this plus some really ugly error term. But they are related. No. So that's something. And of course, the upshot here is that here we do really have algebraic numbers, just not very interesting ones yet. And so I'll just say, I had more, but I'll do that next time, that our goal now is to do exactly what we did today. And in fact, I'm not even going to tell you how to do it. I'm just going to tell you, go through all of the steps again for today, and change SL2Z with SL2Z1 over P, and it still works. The only thing is that you get infinite sums of rational functions, so you have to make sense of convergence of that, and that will take place in the set of meromorphic functions on the upper half plane. So the goal for next time is to enrich this construction p-adically. Meaning we will consider p-adic limits of these values. And of course, p-adic limits will lie not in L, or L star, but in a completion of it. And so there's more room. They're allowed to converge to something that is still algebraic, but maybe in a finite extension of L, and hopefully in a abelian extension, and we have all of the same properties of singular moduli. But that remains to be seen, and I owe you an explanation of that next time. Okay, that's it.
Question for Sean?
So L was constructed as, I don't know, joining the roots of F1 and F2.
Yeah, that's right.
But as you're arranging through the class, the narrow class group, you're going to be changing the F1s and F2s. Are you going to get a larger field, or are they all going to...
They're all in the same field. Yeah, and that's because, you see, if you have something of any form of discriminant delta 1, will have its root of the form minus b plus the square root of delta 1 over 2a. And b and a are integers, so this will always lie in this field q adjoined square root delta 1, which I called k1. So it always lies in the same field. Yeah. Yes?
Are there any algebraic properties to that? You would call it a pairing if there were any. Are there?
Any algebraic properties?
Yeah, or is that just a map of sets?
It's weird, right? Because there isn't that much structure to play with. There's no relation with the group law as far as I know. So the group law on the class group here and the multiplicative group law here, I don't see any relation there. It would be strange anyways, because you would expect any element in here to have infinite order, and these things have finite order. So it's not a homomorphism, that's clear. But if there's something more subtle than that, I don't know. The only thing I can tell you is that it's anti-symmetric. Meaning, if I change this construction, that's a highly non-obvious fact, where I take instead the cocycle associated to the second guy and evaluate it at the first guy, I get 1 over the previous number. So I get the multiplicative inverse. Yeah? And that's in accordance with what Gross and Zagier saw, because they were considering j tau 1 minus j tau 2. If I switch t1 and t2, or tau 1 and tau 2, I get minus that. But that's an additive theory. We have a multiplicative theory, so we get, instead of minus, we get multiplicative minus, which is a goes to 1 over a. So yeah, these two, that property somehow, and also the fact of the SL2Z invariance, these two properties make this thing kind of smell like differences of singular moduli a little bit, except they're much too arithmetically poor at this point, because they're just in the biquadratic field. But next time I'll enrich that.
How you got that inspiration to consider this construction
Hmm.
and to use it in the p-adic setting?
Yeah.
Do something useful?
I mean, I don't know if Henri knew about the work of Knop, but I definitely didn't. But there was a much more recent paper of Duke, Imamoglu, and Toth, beautiful paper actually, about linking numbers of modular geodesics, modular knots is a better way. So what they do is they sit inside of the unit tangent bundle of the universal elliptic curve. And what you could do is this unit tangent bundle has a very nice structure in that you can write it. So it's a long story actually. I don't know if I should tell you, but so you can look at SL2R modulo SL2Z, which is that unit tangent bundle. So if I quotient out by O2R on the right, I get the modular curve. Yeah? But I haven't done that yet. So I'm sitting inside of this tangent bundle. And this thing is diffeomorphic to a 3-sphere, so S3, minus a trefoil knot. That's a very nice observation. It's a very classical one. I don't know really who it goes back to, but it appears already in the work of Milner in maybe the 60s. So we get S3 minus a trefoil knot. So I'll do my best to draw a nice trefoil knot. So S3 minus the trefoil. And what you could do is this S3 minus the trefoil, by looking at the left-hand side, there's this very nice flow on this threefold, which is the diagonal geodesic flow. I can write it down, but it doesn't matter so much. So there's a natural flow here coming from the fact that you can diagonalize things and then you kind of put in a parameter and that gives you a closed loop whenever you follow along a hyperbolic matrix in here. So any hyperbolic matrix like F1 and F2 will naturally give rise, by following this flow, to some kind of knot inside of this surface, and it'll be closed. Yeah? So it'll actually be a knot. And then so that's the one coming from F1, and then F2 will maybe also have one, and maybe it'll do something more complicated. And now it's become so complicated you can't see my picture anymore, but nonetheless, I have this F1 and this F2. So Etienne Guis, in his ICM address from 2006, he addressed the question, if I just take one hyperbolic matrix and I take this knot, what's the linking number with the trefoil knot? And that linking number he expressed in terms of this Eisenstein cocycle that I had on the board in the beginning. So he gives a kind of a procedure from this Eisenstein cocycle to get that linking number. And what Duke, Imamoglu, and Toth did is they asked a very natural, beautiful question of what happens if we ignore the trefoil and we take two hyperbolic knots? What's the linking number they have with each other? And they expressed this linking number in terms of this Knop cocycle. And that's where we found out about this Knop cocycle, and then it felt natural to try and do this p-adically and evaluate it in this way. So it really came from this work of Duke, Imamoglu, and Toth, which is super interesting by itself, but it goes in kind of a different direction, is that it's trying to find the linking numbers rather than these algebraic invariants that we're hunting. But they come somehow from the same object.
Questions?
Sorry. Is there a deep difference between the multiplicative and the additive theory, or is it just convenience that it is well?
No, there's actually a very important reason that we need to have a multiplicative theory. So there's a very important, profound difference between the two. For instance, I mean, we could ask ourselves, would it even be possible to do this whole theory additively, which could be another way of interpreting your question? And the answer is definitely no. And the reason is that, you see, singular moduli are very bizarre objects, and I already told you, they have very smooth factorization, so they can be absolutely huge numbers, gargantuan as one might say, but I've already gotten a lot of feedback on that choice of words, so I hesitate to use it again. Anyway, so these are both very smooth numbers with the property, and that's what Gross and Zagier discovered, that their difference is still very smooth. And that's bizarre because that kind of thing shouldn't happen all that often, additively speaking, in the sense that if I have three numbers and they're all integers, let's say A, B, and C, and I have the relation A plus B equals C, then if they're all smooth, that should be essentially never occurring. That's what the ABC conjecture says. It says it's extremely rare to add two smooth numbers and still get a smooth number. So you might try and think of breaking this conjecture, by disproving it, by saying, well, I'm going to take for my A j tau 1 minus j tau 2. And now I'm going to take for my B j tau 2 minus j tau 3. And then my C is j tau 1 minus j tau 3. And if I pick tau 1, tau 2, and tau 3 to be CM points of class number 1, I know all these things are going to be integers, and they're all going to be smooth. So it looks like I might be able to break the ABC conjecture. Unfortunately, there's only finitely many CM fields with class number 1. So you only get a handful of examples of this, and you can't really break the ABC conjecture. Now, we're dealing with real quadratic fields. And for real quadratic fields, the situation is wildly different. So already Gauss noticed that, in fact, a huge proportion of real quadratic fields have class number 1. So if we were able to make an additive theory like this, we would break the ABC conjecture. So we're not allowed to have an additive theory. So then we settle for a multiplicative one. Sure, yeah.
So I'm just trying to understand the analogies between this construction and the original construction.
Yes.
So in the case of rank 2 lattices, when we did the multiplicative lift, what we got in the end was not periodic anymore. Right?
No.
We lost some properties.
Exactly.
In this case, what are the properties that we are losing?
Yeah.
Are we losing any properties?
In that setup of z squared? In this setup. No, in this setup, the situation is somehow almost nicer than the setup of the elliptic curve that we considered in the beginning. Because for the elliptic curve, we did a similar kind of procedure. Everything was in H0, not in H1. Nonetheless, H0, and then the group was z squared, right? Because it was a lattice acting by translation. And then we were going from kind of meromorphic functions additively to multiplicative meromorphic functions. And we saw that the sigma function, this lift we wrote down, was not invariant. So we might think, oh, maybe we do the same cohomological hunt, and we find out that actually there was a secret lift that was invariant, but that wouldn't work because H2 of z squared is much bigger. So ironically, z squared feels like a much simpler group than SL2z, but cohomologically, SL2z is a lot simpler somehow. So there, of course, everything is shifted down by 1, right? So we're going from H0 SL2z multiplicative functions to H0 SL2z of multiplicative functions modulo constants, and then to H1 z squared with values in C star. And that's a much bigger group. That's just homomorphism, so you can pick two complex numbers freely, and that's precisely the kind of complex numbers that we saw. So in some sense, the situation is more difficult in the case of the elliptic curves. But we're going to pass next time from SL2z to SL2z 1 over p, and then this H2 is much richer, just like in the case of z squared. So then some non-trivial lifting abstraction can occur. Yeah. Yes?
Can you also evaluate the Einstein conceptual?
Yes, you can. And if you do that, you get essentially the fundamental unit in the real quadratic field where you evaluate. That's also an exercise. If you look at the notes that will be linked on the website, that's one of the exercises, actually. It's a very instructive exercise to do. So also there, the special values are algebraic. They're just not super rich. They're always a fundamental unit, or like a 12th power of the fundamental unit, something like that.
Maybe we can talk with
Sure.
John later, but we are pretty late, so thank you again. Continue at 11.
This is the matrix from the fundamental unit of the order?
Yes, that's exactly right. Yeah, that's exactly right. Oh, thank you. Excuse me. Yeah. So F2 secretly defines an embedding of K1.
Ahora ya está todo siendo escuchado.
Perfecto.
Right now, I'm in a transition phase. That's why I decided to shift the second shift to
That's the status of the guy.
Yeah.
His WhatsApp number. Crazy people. Then there's some video of him.
lunch, we all
It was fun.
parts of India would without looking?
Parece que está medio gastadito este como...
¿Eso ya está?
¿Cuál usaste para el
Yo no sé. ¿Fue este o otro? Ah, está bien.
No sé, tal vez del más cargado que siempre vamos a usar.
Listo. Si alguno no funciona, me dice si lo cambio. Listo.
Okay, so we continue the morning session with the third lecture of 1.
Okay. Well, thank you again for being here today. So, yesterday, we called that we construct this category of condensed abelian groups. We mentioned a little bit some properties of this category. It was a very nice grothe-adic abelian category. You could realize topological abelian groups inside them, and somehow at least some mapping spaces between these topological abelian groups, they coincide with something that we already know from topology, meaning that the mapping spaces just are given by a topological space using this compact open topology. We also saw something. So yesterday I'd like to use something at the end. I'm going to make a correction right now. So yesterday we took X, some locally compact Hausdorff space. And I say that, well, for M, some abelian group, this condensed cohomology was the same as the shift cohomology, which is true, which is correct. And then I claimed something that was wrong, meaning that if you take the right category, with the positive right category of abelian shifts, it stopped that it was equivalent to this category of this condensed site, where this X-cond was the category of, was the site of profinite sets mapping to X. Profinite sets mapping to X, or maybe compact Hausdorff spaces. So it's not true that these two are the same, but the content of, let's say, this comparison is saying that you have a fully faithful map. And this is basically saying that anything that comes from a shift in topological spaces, whenever you compute this Ohm complex between the shifts, either in topological spaces or in this category, they are the same. And this precisely translates, at least in, this is a particular case of this phenomenon. So this is the correct statement. Sorry about that. Okay. So yesterday we also mentioned that this category of condensed abelian groups has a tensor product
which again is not special for condensed abelian groups, something that happens whenever you take sheaves on a site. But this tensor product was still like too algebraic.
Maybe you went over this in the first day, but how do you quantify something being too algebraic?
I can tell you exactly what I mean by this. So this means that if you take M and N to be condensed abelian groups, and you take this tensor product, and you just try to look what happens in the underlying abelian group of the condensed abelian group, this is just the usual algebraic tensor product of the abelian groups here. So for instance, if you take M or N to be things like p-adic integers or the real numbers, you will get maybe a condensed ring by taking this tensor product, but it will be a very weird condensed ring whose underlying topological space is just the algebraic tensor product of the QP with QP or the real with the real. So something that, well, certainly we don't want this when do analysis or analytic geometry. We actually want to have some notion of a completed tensor product. So we want some notion. So there are different answers to this question because there is not just a completed tensor product. There can be different completed tensor products. And let me maybe first summarize the three most fundamental tensor products that you construct in theory of condensed math. And then we will come to focusing one of them. Yeah, so I would say that the most important tensor products so far are so first, maybe the first one that was constructed is something that Clausen and Scholze called the solid tensor product, which is very good to do let's say algebraic geometry, to do non-Archimedean analysis, but for the real numbers, it just kill them. So basically, well, whenever we're going to be more precise what this category is and how do you construct this tensor product, but basically this tensor product, whatever you do and you plug the real numbers into here, you're just going to get 0. So this one just completely isolate the real numbers outside and just focus in purely non-Archimedean features. There exists another tensor product, which maybe was constructed after the solid tensor product, which is these liquid tensor products. Yeah, here the names become funny. And this tensor product is actually something that lives for both Archimedean and non-Archimedean analysis. So it's some kind of tensor product that specializes in I mean, there has not a distinction between being p-adic or being real. For both of them, there is a notion of this liquid tensor product. And maybe it's worth to say that in the real case, it is closely related to these spaces of radon measures that I mentioned also as an example yesterday, but maybe some non-locally convex variant of them. So this is related to some non-locally convex but still somehow P convex for P some number between 1 and 0 vector spaces, topological vector spaces. Well, so this tensor product is good for do things like differential geometry. also complex analytic geometry, and maybe, well, this one is better suited to do like adic spaces and rigid geometry, but this one is also good to do just Berkovic spaces, so some kind of overconvergent theories of spaces. So this liquid is also very, very nice. And the last one that we're constructing in the course is this gaseous, which is there is a 100% chance that I just misspelled the word, I think. This gaseous tensor product that somehow is an universal tensor product or universal completion that admits a pseudo-uniform Miser. Or you could say a norm as well. Or I think this one is doesn't work very well. What did I take? It was supposed to be another color. So, well, somehow this tensor product and this tensor product, they are just specializations of this one. So this one is, in some sense, like a most universal tensor product. Well, at least once you put some conditions in the rings. So this one is also very good to do things like complex analysis, complex analytic geometry, and rigid analytic geometry, and so on. But maybe this one is not so good to do differential geometry. This one is better for some completion reasons. So these things, for example, if you plug in things like Frechet spaces, nuclear Frechet spaces, these two tensor products are going to agree just with the, maybe this one most often, is going to agree just with the usual projective tensor product of Frechet spaces. So this one recovers like classical tensor products that have been constructed a long time ago. So for today, and maybe the rest of these next talks, we're going to focus in this solid tensor product, which is the one that is maybe of easier access. Okay. Should erase that. So today we focus on solid and the tensor product. Okay. So in order to define this tensor product, we first need to define, well, what means to be completed, right? This is a completed tensor product, but completed in what sense? So for that, we need to introduce this category of solid abelian curves. So in order to understand this category, let me maybe recall a kind of idea that we have from non-Archimedean analysis. Which is the following. So in non-Archimedean analysis, null sequences, so sequences that go to 0, are precisely, okay, thank you. The summable sequences. And what I mean by this, well, for instance, if you take some kind of sequence in QP, then there is this very classical, result in p-adic analysis saying that this sequence, this sum, converges if and only if this sequence goes to 0, something that is very wrong and not true in the real situation. But in p-adic cases and non-Archimedean analysis, we have this kind of easy way to check that something is going to converge, just by knowing that the elements are just going to 0. So building on that idea, we can actually define in kind of a natural way this category of solid abelian groups. So for that, we first need to make sense of what it means to be a null sequence. So let me do that. So consider this space P, condensed abelian group that, well, we saw since yesterday that, or 2 days ago, that there exists a profinite set that just parameterizes sequences that converge. Because, well, a sequence that converge is just, again, something like this that eventually has some kind of point. So it was this space that we call just n with infinity, with some topology such that the neighborhoods of infinity are just up, but finitely many integers here. So we first can just try to look at a condensed abelian group that parameterizes sequences that converge. So this is easy. This is just taking the free condensed abelian group of this profinite set. And then if we want to take null sequences, well, the thing we need to do is just kill the limit point. So for that, let me do this. So kind of by design, given, for instance, a topological abelian group, if we take maps of condensed abelian groups from this P to maybe the condensification of A, this is precisely, well, again, by construction, the space of null sequences. Okay. Maybe just let me say Hausdorff.
I'm having some slight confusion in trying to understand how you're viewing P as a condensed abelian group. Like, how do I view it as a P?
Because this one is the free condensed abelian group generated by this profinite set. Okay. Right. So this is not like the free abelian group. It's the free condensed abelian group generated by these guys. The functor that we saw yesterday. So again, like by design, by adjunction, you can just take this interjunction between condensed abelian groups and condensed sets. You have yesterday. This one is precisely just this space of null sequences. So from that, we can just define well, like basically the same space for any condensed abelian group. And let me mention a couple of remarks. So definition. Given M, some condensed abelian group, it's a space of null sequences is the condensed abelian group, because again we want to keep living in this underlying world of condensed abelian groups. Null of M, which is just given by, well, basically the formula we have there, just the internal home of this object P towards this object N.
I have a question. So
Yep.
you are viewing this homomorphisms from P to, is this an internal home or is this just?
That's a good question. Here I'm taking just the usual homomorphisms because I just want to get a set of null sequences here. But it's going to be much better for us to actually consider the internal home, which is an actual condensed abelian group. So the underlying points of this thing when M is equal to A bar, is precisely the space that is written here of null sequences, which is just a set. But we actually want to recover a whole condensed abelian group.
Sorry.
Yep.
I can see why home is equal to the null sequences of A.
I mean, if you have a map from P to A bar, forget about this. It's the same as having a linear map from this thing to A bar, which by adjunction is the same as having a map from this profinite set to A bar. And this profinite set, by definition, what gives you is just sequences with a convergence point. But then we're killing infinity. So we're asking for sequences with a convergent point, which is given by infinity, by 0, sorry, because we just killed the convergent point infinity to 0. So you will get precisely these null sequences. Maybe we'll leave this as an exercise for you to check. Right. Let me maybe do a couple of remarks, something that we kind of know, or sometimes we just overlook if we're not careful. In general, being a null sequence is not a property of a sequence. But some extra structure. So this means that, well, you have a map from this space of null sequences for which you can just restrict just to the free condensed abelian group generated by n, which is just a n copies of set. Going to take a restriction. And M, which is again just a product of M. And this map is in general not injective. However, for things that are Hausdorff, for which we know that somehow limits, if they exist, they are unique, it is injective. But it is for M quasi-separated. So, yeah, whenever you talk about a null sequence on a space, you need to be careful. Or even a convergent sequence on a space, you need to be careful what that means. It's not it's not just like giving a sequence itself. You also need to give somehow the continuous map from this space to, well, your topological space or to condensate. You need to give the whole continuous map. It's not just the ends, the whole continuous map. Yeah, this is interesting. Okay, so let us use this P, I should know how to erase it, to try to realize this idea that scenes that are kind of non-Archimedeally complete are precisely those objects for which the null sequences are summable. So
It is for M. What it says?
sorry? Quasi-separated. Sorry, let me see. Yes.
So it's like this is not just when the sequence tends to 0, but how it tends to 0.
Exactly. It's important to say how it goes to 0, meaning basically that it's important to know not just from n, but the whole map from these things. Yes. Exactly. So let's consider this guy. This guy, well, you can check that has an algebra structure. This is basically because you can't endow this, the monoid. So this is a monoid. For the addition, where, well, in n, the addition is the usual one, and in infinity, everything is just added, you get infinity. So this becomes an algebra, and this one is an ideal in this algebra. And the class of 1, or the element 1 inside P, and maybe more concretely inside the points of P, gives rise a map of algebras from the polynomial algebra to this object P. So whenever we're going to, so let's say that we also write this object P to be something like a CQ hat, just in order to see this object as an algebra, maybe. So now, given M, some condensed abelian group, multiplication by Q on this spacing here induces a shift map.
Sorry, how does one give rise to that map?
As long as this one is just an algebra, and you have just an element in an algebra, you always have a map of the polynomials to the algebra, just mapping Q to that element, and any power just to the powers of that element. So in this case, for instance, Q to the n is going to go to the class of n, which is the n times sums of U1. So this is going to induce some shift map.
You're considering this map in the category, which category?
All of these things are taken now in condensed stuff, like condensed abelian group, condensed rings, and so on. Yeah, sorry, a little bit trying always to just push everything to the condensed world, unless maybe going to make some precise copy here. So again, all classical objects like sets, rings, abelian groups, they always embed into just the condensed sets, condensed rings, and condensed abelian groups. Tac, tac, tac. Okay, this is bad. So this is a shift map from the null sequences of M to these null sequences of M that heuristically it sends a null sequence AN to the sequence but shifted by Q. That's what's called this, shifted by 1, sorry, and plus 1. So when you look at the underlying sequence of the null sequence, or the restriction to the integers, this is precisely what this map is doing. It's just shifting ANs to just this AN plus 1. It's not, so, well, let me now make the definition. For which I highlight that it's very important that we're working the live setup in order to this to work. So a condensed abelian group M is called solid if the map from the null sequences of M to the null sequences of M given by the identity minus the shift map is an isomorphism. So let me explain why this formulation actually recovers the idea that null sequences should be precisely the summable sequences. So to see that, well, let me just rewrite this map here. Let me write identity just by 1. So let's say that if this map is an isomorphism, then, well, what we're doing here is just sending a sequence an, heuristically again, just to the sequence given by an minus an plus 1. And the way to recover this sequence, and let me call maybe this one just bn. And the way to recover this sequence from that sequence, in case it comes from something, is by taking precisely this bn. And, well, in this case, would be to do a telescopic sum, which is just taking like all these sums like this. So if such an inverse exists, it is somehow encoding the fact that coming from here to here is precisely taking these sums. So let's say that just this is kind of the concrete way you realize this idea of null sequence has to be precisely the summable sequences, just by asking this to be an isomorphism. All right. So this is saying that these solid abelian groups are precisely all these condensed abelian groups for which there exists a unique and functorial way to sum null sequences. Is what is this definition is encoding. Right. So that's a definition. Let me say more about the actual category of solid abelian groups. Should have like this. So let solid be the full subcategory of solid abelian groups. Yeah. Right. Okay, let me erase this so I keep the definition there. Okay, so one of the reasons why this definition actually is very helpful, why they changed the perspective on the definition of solid abelian groups that was done in a different way in the original version, is because of this object P that we use to define these null sequences. So there is a very nice fact on the light world, some proposition. Let's say only works in light math. We say that this object P, that here I'm just considering this object as a condensed abelian group, is internally projective.
What does that mean?
I'm going to say in a second. In condense up. So this means that the functor from P to something, from condensed abelian groups to condensed abelian groups, is exact. The internal home into here. So this is a feature that actually is very useful, which is not true in the general condensed setup. That looks like technical, but actually, thanks to this, is that you can construct a lot of completed tensor products now, which before maybe was like a technical problem that was very difficult. But with this now you can just do it. So thanks to this property of the subject P, you can deduce just formally a lot of very good properties for this category.
Before you erased,
Yep.
you did the map of identity minus 2
Yes.
and the inverse. I cannot see why this is not an isomorphism for all condensed abelian group. Can you show me an example that where it fails precisely and it's not solid? Because you just wrote the map and it's inverse.
So I can tell you an example of this map is not an isomorphism, and if you put m to be the real numbers. The reason is because if it has an inverse, then they will say, because of the discussion that we have here, that any null sequence in the real numbers is actually summable. But this is not true, because, for example, you have the sequence of 1 over n, which is the harmonic sum, which is not convergent.
Also, it fails in the convergence of the telescopic.
Well, in the sense that here you will have a null sequence, which doesn't come from something here. For like the 1 over n sequence here, this harmonic sequence is not coming from something here in the case of the real numbers. So it is not an isomorph. It's not surjective.
All right, perfect. So this is always injective.
I think it's always injective, yes, because you can recover the original one in the telescopic sum, at least for separated things. Yeah.
I actually don't understand why you're saying that, like where is light condensed not appearing in the actual statement of the proposition?
In the sense that it is false in the condenser, in the general condensed setup. This proposition is just false. It is only true when you work in this light setup. And for that, it's kind of very important that we have control on this category of profinite sets, which are not like very wild. They're kind of just countable limits of finite sets. So the proof of this requires like being able to just write everything as a countable limit of profinite sets.
Right, but so did you mean homomorphisms from like this map from condensed abelian light to condensed?
Yeah. All of this, yes, sorry. I should have saying that again at the beginning of the talk, that now we're all working, we're going to keep working in the light setup.
Okay.
So if I would like to be like much more precise, I will need to write a light here and light here. But I just want to avoid writing light for all these things here. But yes, this is only for the light setup.
And P can also be regarded as a light condensed abelian.
This one is a light condensed abelian group because this is just a free object in a light profinite set. Okay. So
the other results working as well in condensed map, and that's the first case where it only relies on the.
right. So this is one of the first and basically very important result that only holds in the light setup, that does not in the general condensed setup. This is very important. Because like otherwise the definition of this condensed abelian group of solid modules is very different if you do it in the general way. It's completely different. But this one gives somehow much more clean definition that also follows the intuition from non-Archimedean analysis. So this definition, you cannot do it in the general setup. Okay. So let me just erase this. Keep the definition of solid abelian groups in here, so we don't forget what it is. This to be an isomorphism. So first theorem that you get for free, essentially, is the following. So the category solid inside condensed abelian groups is stable under limits, colimits, and extensions So in particular, it's an abelian category. Like moreover, the following holds. So the first property that we're going to hold is that, well, again, by abstract category theory, this one is a subcategory stable on the limits and colimits. Then this inclusion is going to have a left adjoint, just because stable on the limits. So there exists a left adjoint with inclusion. A left adjoint to the inclusions of solid inside condensed abelian groups. That we denote, maybe first way to denote it is just by taking a box as an upper index. And you should think about this box basically as taking some sort of non-Archimedean completion. So this one is morally some kind of non-Archimedean completion. Shouldn't use this. So second property is that, well, this functor, which again is some kind of non-Archimedean completion, is killing the real numbers. So in particular, the real numbers are not solid, and it makes sense because again, this is taking some condensed abelian group and kind of completed to something for which null sequences are summable, and this is kind of the most extreme case where null sequences are never going to be, are not in general summable. So the real number is just going to kind of kill by this functor. And in consequence, as we will see in a second, all modules over these are going to get killed on this functor.
But there are like lots of null sequences, like from classical
Yeah.
that converge, that sum up in real numbers, right?
There are a lot of sequences which converge, which are summable, yes, but not all of them. And this one is requiring for all of them to be summable. So this is what makes this file. There will be like variants, like this liquid tensor product, the gaseous tensor product, which are going to ask for kind of a summability of a sequence that decays exponentially somehow, which is something that we know that it holds for the real numbers. So this is why kind of this, for making this precise, you're using this guy. So that's why this guy is quite convenient to have. But let me not go to many technicalities and just mention 2-3 features. The integers. So the integers are discrete. Well, something discrete should be somehow non-Archimedean incomplete because null sequences are just sequences that eventually go to 0. So yes, these guys are precisely solid here. And actually, this category, one can prove that is the smallest category in condensed abelian groups, stable under limits, colimits, and containing set. So in other words, like being non-Archimedean complete basically tells you that you can write your object as a limit of colimits or limits, of the integers in some sense. So the integer is like the most simple thing that is not Archimedean complete, and everything else is kind of built up from them. So let me maybe first give an idea of this first claim and why you expect at least to give a very rough sketch of these two aspects of the theory, which are very fundamental. just erase what I wanted to erase. Anyway, so for example, for stability, so sketch the proof. Let's say that for stability under extensions, well, you just consider your short exact sequence of condensed abelian groups, where m prime and m double prime are in solid. But then, because P is internally projective, you also will have a short exact sequence in the null sequences. And then, well, you're considering this map, which is 1 minus shift. That, of course, is functorial. And you know that this map is an isomorphism of these two, so it has to be an isomorphism of this one, just by and well, the stability under limits and colimits is basically proven in the same way, where you use that P is internally projected to make it maybe I should say something else, plus compact. So you can make it commute with colimits as well. And basically, because these null sequences commute with all limits and all colimits of this object M, then again, this stability under limits, colimits, and extension is just going to be formal by essentially the same sort of argument that appears in here. And this automatically is going to show that this one is an abelian category, because, well, the co-kernels is a co-limit, a kernel is a limit, and these ones are stable under this condition. And, well, whatever you have to check for being an abelian category. As I say, like the synthesis of this left adjoint is something formal, followed from category theory. And let me maybe explain the 2 and 3. So for 2, well, you can construct a null sequence. So in this guy, you have a null sequence that is like 1, 1/2, 1/2, 1/4, 1/4, 1/4, 1/4, and so on. So this is a sequence that goes to 0. But if you try to sum the sequence, you will see that, well, this is going to explode. It's going to give you like infinity. So the idea is basically that, well, you have this kind of element here, that in here, you know that you can sum it. So this object, this sequence will have a sum in here. But you can rearrange this object in a different way. So by just adding maybe these two, and then these two or these two, and, well, you add just by pairs what follows, you will see that this object x, you can write it down as 1 plus, well, when you add this one and this one and this one, you also recover the same object x, like x. And, well, once you have this, and this one is going to be an algebra, to prove this. So you will have an algebra where 1 is equal to 0. And you will get this. I'm going to see maybe in a second why this is actually an algebra. And again, like the idea for proving the part 3 is what I just mentioned at the beginning. Like this one is discrete. So a null sequence is a sequence that is eventually constant equal to 0. So, and this is just a finite sequence essentially, and any finite sequence you can just sum because it's just finitely many elements. So proving that this one is in this category is also just an easy computation you can make there.
I'm sorry, you write an exact sequence for null sequences, but I can't see clearly what is the left adjoint in this case, because you are supposed to start with a condensed abelian set.
You mean this functor?
Yes, and
Yeah, this one I haven't yet discussed how it looks.
sorry?
I haven't yet discussed how this functor looks.
All right.
Yes,
I thought that you started with the one. And
No, these one are just solid, so this means that this one are isomorphism, these operations, which implies that this operation is also going to be an isomorphism here, like this endomorphism. But I haven't yet talked about this functor. I'm going to do it now.
all right.
So recall that the motivation to defining these solid things was in order to have some notion of completed tensor product. And well, so far we have a notion of completed abelian group, but maybe not a notion of completed tensor product. But it turns out that actually you can define a completed tensor product just by taking a naive tensor product and then taking completions, which is maybe not the way to do it. So moreover, this category has a unique symmetric monoidal structure. So let me just say tensor product. Making this functor symmetric monoidal. So this means basically that the way you compute this completed tensor product is exactly what you said before. So if you have two solid abelian groups, you can compute or just define this completed tensor product by taking the naive tensor product and then taking completions, which is, well, maybe some natural way to try to define a complete tensor product once you have a notion of completion in some sense. So, well, because of that, in particular, like when you take this functor, we call it solidification. So once you have this kind of symmetric modular structure from the functor, it's going to send like algebras to algebras. In particular, this one is going to be an algebra here. Okay. So now let me tell you how solidification looks for, again, the key objects, which are profinite sets. And maybe saying some words about other objects. How does this thing look like? So this will follow from some proposition saying that if S is some kind of light profinite set, and maybe for this one, let me stress the word light here. So otherwise, I think that could be some problems. Then if we take the free condensed abelian group denoted by this S, that recall that has some kind of description, something like this. Maybe let me write S as a limit of finite sets. I recall that this one yesterday, I think it was yesterday, we saw that it has some kind of description as some union of profinite sets that were just explicitly constructed using the coefficients on finite sets. So when you take the solidification of this guy, this is just isomorphic to the limit of these free abelian groups on the finite sets, which I recall is the same as the dual of the continuous functions from S to Z. So taking solidifications of profinite sets is in some sense taking a space of measures for the profinite set with the set of set value Razon measures from the profinite set. So this is what this solidification is doing. in the original approximation to condense mathematics to solid abelian groups, well, the way you define solid abelian groups was precisely by defining the free objects in this way and trying to spread out this definition to more objects. Well, in here, you go the other way around. You first give a definition that for formal reasons has very good categorical properties, and then you compute what these objects look like. Right. So let me maybe do a, well, just state a lemma saying that actually this category of solid abelian groups is in some sense quite simple. Lemma, let S be a profinite set. Then the continuous functions is a free abelian group. And maybe I will let you do an exercise to prove it when the profinite set is light. It's not so difficult once you write it in this way. So in particular, we have an isomorphism between these solid things and a product of the integers that maybe I is a countable set. Could be finite or, well, depending on finite or not finite. So it's saying that the solidification of all these free objects on profinite sets are just look pretty much the same, just kind of products of copies of set. So for example, recall that we have this P that I wanted to look as some algebra C of Q. And if you take the solidification of this algebra, you will get this power series ring on the variable Q. And this object P was compact and internally projective. We know that this object set of S generate all condensed abelian groups. Then you will get a corollary that let me just squeeze here on the left. Is that the category of solid abelian groups has a compact projective generator given by just a countable product of these copies of set. Which is very different from what happened in condensed abelian groups where there is not compact projective generators. So there we don't have these things. But here everything is kind of just kind of freely generated by this guy. Okay. Yeah, so let me give a couple more examples of of solid abelian groups that show up, and maybe some examples of some tensor products between solid abelian groups. So, some examples. So maybe the first one, which is an interesting example, is that, well, in which sense the solid tensor product is complete? It is complete maybe in the following sense. If you take just countable copies of the integers with itself and you take the tensor product, well, something that you would like to be true is this one, just to put the two products inside. And you can do it. So indeed, you get something that is complete at least in some concrete sense. You have the p-adic integers, right? So this one is just a profinite group, and actually you can write it down as a limit or something like this. As I said, Solid is stable on the limits, co-limits. These one are just quotients of the integers. The integers are solid, so this one is solid. And then this limit is also solid, so this one is solid. And you can compute these solid tensor products between set P and set L, and you get exactly what you expect. You get 0 if P different from L, and you get set P precisely if P is equal to L. It's a good computation because, well, this is exactly this kind of thing you would like to guess that you get whenever you take some kind of completed tensor product with these two guys. So this kind of follows from this. Okay, I think I still have like a couple of minutes. So let me maybe give a little bit more examples and motivate what's coming next talk. Right. So another example that maybe comes from p-adic analysis is the case of Banach spaces. So basically, consider a completed direct sum of copies of QP. So this is something that you can kind of write down using the topology and taking the underlying condense abelian group for the topology, and well, you can get it. But another way to just write down this is as follows. You can just take the limit of a direct sum of set mod P to the n, and then you just invert P, which is also a co-limit of multiplication by P. So this just gives a presentation of this direct sum that realizes this as a combination of limits and co-limits of the integers. So in particular, it's a solid abelian group, or going to be a solid cube vector space. So then, if you take this tensor product, you tensor with this guy. Again, usually you would like to have like a completed tensor product of Banach spaces, and this is what you get actually in this solid tensor product, which is precisely given by this guy here. So something important to highlight in here is that this computation is actually non-trivial. This one is actually more trivial. And this computation requires writing this direct sum, this Banach space, somehow as a union of profinite sets. Basically, whenever you have a Banach space like this is just sequences that go to 0, because we are in an Archimedean world. And sequences that go to 0, you can always like write it as a union of products of copies of set P, just all possible products of sequences of set P that go to 0, or maybe elements in set P. And once you have such a presentation, well, you need to do a little bit of an argument, because at least for those objects, you know that it behaves like that, and you can use this. And then you kind of recover this one here. So somehow, from this perspective of condensed mathematics and solid Abelian groups, like Banach spaces are more strange than maybe these Smith spaces that we mentioned last time. And this is not only going to happen in this world, it's going to happen also maybe in the gaseous and in the liquid world as well. Like Banach spaces are very tricky. Well, these ones are much easier, just to maybe let me finish with the last funny example, and I promise I just finish here. So now you have, that takes X, let's say a CW complex, right? Just some topological space built up from just balls by gluing stuff. Then can consider the free condensed abelian group attached to the object X. And, well, something that I didn't mention, because of lack of time, is that this solidification functor is, again, some left adjoint, is going to preserve right exact sequences, so it's going to have a derived solidification functor. It's going to extend to the right categories. And if you do that to this thing, that maybe just put an L, meaning that kind of derive. This is the derive solidification. Well, you get a complex that is quasi-isomorphic just to the chains. I forgot how to write it. Chain complex of fixed values in set. So in particular, this thing, the HIs that I should write down, maybe, let me write homological notation, is computing precisely the homology singular. The homology of this space X, the CW complex. So even though like we did something that killed everything that was non-Archimedean, well, still we can recover funny objects like this singular homology just from the solidification of this free condensed abelian group generated by the object X. So it's we'll say a very elegant way to just recover this kind of invariance just from an actual free object on the space. Okay, I think a little bit over time, so thank you very much.
Any question for fun?
If you replace Z with any other abelian group,
Mm-hmm.
what can we expect to see?
Yeah, this one, once you have it with set, and you do, well, you just tensor with M. So if you do something like this, and tensor with M, maybe derive as well, then this one is just recover the homology with the coefficients, just by doing the base change of this case of the change here. Yeah, so this is already true if you do just with the chains. You base change this with from set to M, and you just get homology with values in M.
And how do you make sense of that derived tensor product?
Right. So condensed abelian groups, they do have a derived tensor product. So that's a good question. So in here, you have this derived tensor product in here. Just again, because it's a sheaf, what's it called? It's, again, just the right category of, what do I want to say? Well, basically because it just shifts in a site. And basically a shift generated by flat objects is going to be flat, this category. So in particular, for example, the set S are always flat, and everything is built up from this one. So you can just derive the tensor product in here. You can extend the definition of solid abelian groups to the right categories by the same formula, and actually it's going to give you a fully faithful embedding, something stronger, of this guy in here. This fully faithful embedding also preserves limits, colimits. So it's going to have a left adjoint that is going to be precisely this derived left functor of the solidification. And similarly, as we define the solid tensor product as just the completion of the algebraic tensor product, then you will be able to define this one just by taking the derived algebraic thing and just taking this solid completion. And this one is going to give you this solid tensor product. And it turns out that actually this computation is also true if you put an L, which is actually very good, because showing that these guys are I mean, you know how to compute these guys. And moreover, you can also prove that these ones are flat, which is also false for the general condensed math, but it's true for the light condensed math, that these objects are flat.
Question?
In the tensor product, what do you mean about the L in beyond the tensor product?
You mean this?
Yes, exactly.
This means that it's a derived tensor product.
No. The unique tensor product, so that you have the You said unique tensor product earlier.
I mean, in the sense that tensor product is some operation that is right exact, in the sense that sends a short exact sequence to a right exact sequence. And whenever you have this kind of functors in abelian categories, which are nice, like Grothendieck abelian categories, you can always derive these functors, maybe up to some kind of conditions, which means kind of replacing an object by a resolution of, in this case, flat objects, and just take the tensor product of this resolution. And this is going to give you the derived tensor product. And this is what this L refers to. I think that compute these Tor groups.
Give an idea for a proof that integers are solid.
Sure. So the thing is that what you need to do is to compute the space. So for that, you want to compute the null sequences of the integers. And as I say, like a null sequence, well, at least when you evaluate at S, is the same as some kind of maps from this P tensor set of S going to set that you can recall that this P is just this infinity minus 0 minus infinity S. So at the end, what you get from this space of null sequences are the same as just kind of maps from S copy infinity cross S going to set, which send maps like this, such that F infinity cross S is just 0. This is exactly what this space is. But any such a map from profile set to the integers is locally constant because this is discrete. So this one is locally constant. So because it's locally constant, you can prove that this space is nothing but a direct sum of just the continuous function from S to Z. And once you have this presentation, then you know what this null sequence is. It's just a direct sum of set. And for this one, just proving that 1 minus shifts is an isomorphism is just, let's say, it's just a very easy computation. It's just telling you that you can sum finite elements.
Okay, well, we thank Juan again. We resume at 2 o'clock after lunch.
Yep. So this means that sort of case is not exact. Right. Can you give me an example of short exact sequence that it's easy to see by that as a case?
I can try.
Some funny. You have something like this.